I want to point out first that bad stuff is happening now. There are bad bail and parole decisions being made because people type the wrong number into a black box model, and it's letting dangerous people go free, and it's keeping people in prison who don't deserve to be there. We have bad medical diagnosis and screening algorithms that pay attention to like the parts of the image that are not medical, right? Instead of the medical content of the image. We have bad loan and credit decisions being made based on factors that are not allowed and on faulty information. And I claim that explainable machine learning perpetuates this problem. Now, I want to make a distinction between interpretable machine learning and explainable machine learning. It sounds almost the same, but they are very, very different. So an interpretable machine learning model obeys a domain-specific set of constraints that makes its computations easier to understand. So these are models that are constrained. So interpretable machine learning is when you use a model that is not a black box. Whereas explainable machine learning is when you use a black box and then you try to explain it afterward, like with a post hoc explanation. So you might start with a black box, you would maybe create another model that approximates it or compute derivatives of it or visualize what part of the model or the input the model's paying attention to. You basically find some excuse for why it's okay to use the black box model. Now, so these are very different. And like I said, they sound almost the same, but I think there's really a chasm between these two, right? With one group saying, no, we've got to, we have to use our black boxes because they're more accurate. We just need to explain them. And then you have the other group that's like, no. We can do this all with interpretable models. Okay, so why are these things so different from each other? Well, the arguments in favor of interpretable machine learning is that we don't need black box models in the first place. Also, explanation methods lend authority to the black box, and they're flawed. So I put this slide up a minute ago, but I want to get back to it. This article is about a man called Glenn Rodriguez, who was denied parole because his COMPAS score was miscalculated. So COMPAS is a black box model that predicts future crime. It's used across the United States in our justice system. And he realized after his parole was denied that there was a typographical error in his score sheet, like his criminal history features were just wrong. And it was too late by that point. His parole was denied. There was nothing he could do about it. So now, do we really need to have black box models? Are they more accurate? Well, we took data about the COMPAS score and data from Florida, and we actually did a comparison. So we compared the accuracy of scores from the black box proprietary model with scores created by our latest machine learning method at the time the data set was released, which is called Corals. And Corals produces certifiably optimal rule lists, which are sort of one-sided decision trees. And it's a very complicated algorithm, but it produces really tiny little models. So let me show you the machine learning model that Corals produces. And I can do that because it fits in the bottom of a PowerPoint slide. I'm going to put the whole model right there on the slide. Okay, so the model says if the person's age is 19 to 20 years old and they're male, then predict arrest within 2 years of their COMPAS score calculation. Else, if their age is 21 or 22 and they have 2 to 3 prior offenses, then predict arrest within 2 years of their COMPAS score calculation. Else, if they have more than 3 prior offenses, predict arrest, otherwise predict no arrest. And we thought, oh my goodness, this is really quite a small model. How accurate could this possibly be compared to like COMPAS, right? This is a proprietary model made by a company. How accurate is this compared to that? And as it turns out, surprisingly, they are about equally accurate. So here I'm showing you tenfold cross-validation results. And you can see the different colors correspond to different folds. And both of these are about equally accurate. And so we thought, that's interesting. Well, okay, let's try to get more accuracy. Let's throw the whole machine learning arsenal at the problem. So we tried all of the machine learning methods. And as it turns out, they all perform the same. And some of these methods produce very complicated models, like they don't even fit on a PowerPoint slide, like boosted decision trees or support vector machines with radial basis function kernels. These are very complicated models. And, on the other hand, at the other extreme is corals, whose whole model is right here in the corner. So, you've got this huge debate in the algorithmic fairness literature about the algorithmic fairness of COMPAS. But the truth is that we just don't seem to need COMPAS at all, right? So why are we still using it? I don't even know. But in any case, we could definitely replace it with something simpler and maintain accuracy. Now, the more work I've done in this field, the more I'm convinced that for high stakes decisions, there really doesn't seem to be an accuracy interpretability trade-off. Lots of people think there is, but there's no scientific evidence for it. So case in point, this image from the DARPA Explainable AI BAA. So here it's supposed to indicate that learning performance is inversely related with explanation effectiveness. But I've always had a lot of issues with this figure, right? It's supposed to show you that, like, if you have a really accurate model, it can't explain very well. And if you have really great explanations, it's not very accurate, right? But there's a lot of problems with this figure. I mean, first of all, this figure doesn't seem to correspond to any real problem. This looks like somebody drew it in PowerPoint, right? There's no like data set associated with this. So learning performance, what is it measured with? Explanation effectiveness? How do you measure that? So I think this figure is just funny baloney. I just think it's just garbage. So now, okay, so let's say that, it seems to indicate, let's say it wasn't phony baloney, right? Then it seems to indicate that somebody used a lot of different machine learning algorithms on the same data set, like a static data set with a fixed evaluation metric. But that is not the way we do data science, right? Anyone who is a data scientist knows that when we do data science, we follow a process like the knowledge discovery and databases process from 1996. So they're the KDD process, knowledge discovery and data, right? So basically what you're supposed to do after you run the machine learning algorithm is you're supposed to interpret and evaluate the results, and then use that evaluation to go back and fix your data processing and make the whole pipeline more accurate. And so the fact is that if you actually understood what you were doing and got better explanation effectiveness, your learning performance would actually go up, not down. So that's another issue with this figure. But even if you fixed yourself to a static data set and a fixed evaluation metric, that curve does not look like this. In fact, it looks more flat, like the corals experiment that I showed you earlier, where we tried lots of machine learning methods and they all performed the same. So regardless of explanation effectiveness, though, it's really flat. So the trade-off just doesn't happen like that. And then also, it didn't even say when they, in this document, it didn't even say whether they were talking about explaining black boxes and this or designing interpretable models. And this is from like our military, like trying to get people to apply to do explainable AI. And they don't even know the difference between explaining black boxes and building interpretable models. So in any case, there is a bit of nuance to this that I want to provide to you. There's really two different types of problems in machine learning. There's problems with tabular data, which look kind of like this, and problems with raw data. So raw data are like images or sound waves or large amounts of texts. And these two types of data they behave very, very different from each other. So if you're working with raw data, like images or something like that, then the only technique that's working right now is neural networks. And that doesn't mean that you can't build something interpretable. It's just that you have to build an interpretable neural network. Okay. Whereas with tabular data, as long as we're willing to do some minor pre-processing, all the methods tend to have similar performance, and that includes even very tiny models like the corals model that I showed you earlier. So just sparse decision trees, sparse scoring systems, like little tiny models, just with only a few variables, tend to perform just as well as the best black box if you have just a good representation of your data. And so it really, the fact that these simple models can be constructed really gives you an opportunity to create really tiny models that are very, very accurate, or at least as accurate as the best black box. So I want to talk about, I'm going to give you an example, actually. I want to give you an example of a machine learning model for a high stakes decision. And that decision is about preventing brain damage in critically ill patients. So let's say that you have an aneurysm in your brain and it bursts. So you have blood, a blood explosion in your brain. Like this is a brain hemorrhage, and just blood everywhere. And you then would go to the hospital immediately, get surgery, you'd be placed in the intensive care unit, and you would get EEG monitors all over your head. And those monitors are detecting for the possibility that you might have a seizure. And seizures are common. About 20% of critically ill patients get them. And seizures lead to brain damage and they lead to death. And so doctors will do a lot to prevent you from having a seizure. They might even give you medication to turn off part of your brain so that you don't get your brain doesn't destroy itself. Anyway, so the only way to detect seizure-like activity is with these EEG monitors. And EEG, so we need EEG to predict seizures to determine EEG duration. And EEG, though, is expensive and limited. Like there's never enough monitors or doctors to go around to read the monitors. And so people are on the monitors for way too long, which deprives other people of monitors that they really might need. And so we really need to predict these seizures in advance so that we can prevent, we could distribute the monitors properly and prevent people from getting seizures. So I worked with neurologists to create a model, predictive model, called 2 helps 2B. And it is small enough that it can fit on a PowerPoint slide, but it's as powerful as our best black box machine learning models. So this is the 2 helps 2B score. And it's called 2 helps 2B because it's 2H, E, L, P, S, and then 2 points for the B. So the doctors can memorize the whole model just by knowing its name. And then the doctor would add up the points based on the patient's EEG, and then those points would translate into a score, and they would give you a probability of seizure within the next 6 hours. Now, I know it looks like something I could have made up, but it is actually not created by doctors. It was created by a machine learning model. It is just as accurate as black box models for this data set. And it doesn't force you to trust it, right? Doctors can decide themselves whether they want to trust it. Also, doctors can calibrate the score with information not in the database so that if the patient, if there's something that's not in the database, the doctor can look at the patient and say, oh, that patient needs to get an extra point because they have this thing, whatever. Also, so as I mentioned, this model, it looks small because there's only 6 variables, but those 6 variables were chosen out of a very large collection of variables, right? That it had to choose from a very large list which 6 of them to pick. And so it's a combinatorially hard problem to figure out how to pick the set of variables that together can predict well. All right, so I'll tell you how we created 2 helps 2B. It's by solving this math problem. Okay, so this is the algorithm that created 2 helps 2B. It's called RiskSlim, and it uses, so you don't have to worry about the math, but I will tell you that this first term in the optimization problem tells you to keep the model accurate and risk calibrated. And then the second term tells you to keep the model small so that you only use a small number of variables. And then this is a set of constraints which says make the coefficients integers, because as you saw in the 2 helps 2B score, all of these numbers are integers, and that comes out of this set of constraints. So it could have chosen any number between -10 and 10. Now, if you are an optimization expert, you would know that this is a mixed integer nonlinear program. It's a very, very hard mathematical program to solve. But my point is that this should be a problem of computer scientists, not doctors. So anyway, now that you So now you have your aneurysm, it bursts, you go to the hospital, you get your surgery, you go to the intensive care unit, you get the EEG monitors placed on you. And now what happens is the doctor looks at your EEG and says, oh, you have this, this, and that. So you have a 2 HELPS 2B score of 3. That means you're high risk. We're going to place you on continuous EEG monitoring for at least 72 hours and start you on preventative medications for seizures. Now, so far, 2 HELPS 2B has been validated on an independent multi-center cohort. I was not involved with the validation. That was done by doctors, by neurologists. And what I'm showing you here is predicted versus true. So you want to be on the axis here. So predicted probability of seizure versus true probability of seizure. And the blue dots are from the study where we designed 2 HELPS 2B. And then green is the validation study. And you can see that both of them are right on top of each other. So they generalize very nicely, even across hospitals. Now, it's been implemented at several different hospitals, and it's resulted in a substantial reduction in the duration of EEG monitoring per patient, a 63.6% reduction. And so that has allowed the doctors to monitor 2.82 times more patients than before, which, according to the doctors, helps them prevent brain damage and save lives. So it's a rare example of a machine learning algorithm used in a very, very high stakes decision-making setting. All right, so I've kind of talked about tabular data, and now I want to switch over to talking about interpretable neural networks, because, you know, people really, this is much harder to comprehend, because the notion of like, what does interpretability mean for neural networks, right? That's kind of challenging to figure out. And like, you know, do we need to explain, or do we need to create a black box and explain it? Or can we actually make the network explain its reasoning process to us? Okay, now a lot of people try to explain neural networks. It doesn't work very well. So here's an example of a particularly bad and very popular way of explaining neural networks. It's called a saliency map. And a saliency map, just all it does is highlight what part of the image the model's paying attention to. So here, the model is, you know, we've created a saliency map for predicting why this image has a Siberian husky in it. And so the algorithm, you know, the saliency map highlights the part of the image that you would expect for classifying a Siberian husky. But then, and you think, oh, great, it's doing the right thing. I think I can trust it now. But then as it turns out, well, let's see what else it's doing. So here is now in this case, the network has classified it as a musical instrument. And we say to the network, why did you do that? And it says, oh, I'm looking at this part of the image. Don't you see? It's a musical instrument. So it's really, you don't really want to trust it now after you see that. And, you know, one thing I'm really worried about is that there is a lot of work in radiology on attention maps right now. And I'm concerned because I don't think attention maps really provide you the reasoning process of the model. I don't think it's sufficient. And that this type of issue is particularly bad for like GradCam, which is a method that's very popular in radiology, where people have seen that it highlights all over the image, even if the network is just looking at one specific little piece of it. Okay, so we were wondering, like, could we design an interpretable deep neural network? And we have a couple of ways that we decided to do this, but the first way we thought of, that we're still working on, uses case-based reasoning. And so it's similar to like k-nearest neighbors. It's like you're looking at a case and you're going to reason about that current case in terms of its relationship to past cases. It's like, well, I've seen this patient before. This patient reminds me of that patient that I've seen a long time ago because they have the similar heart condition or something like that. So here's an example of my interpretable neural network explaining to me why it thinks this bird looks like a clay-colored sparrow. So here, the network is going to pick out different parts of this bird and tell me that it thinks it looks like other parts of other birds. Okay? So here, it's highlighting this part of the image in two different ways. So the head of the bird. So the network is saying, I think the head of the bird looks like the head of that bird, right? And you can see how it does. I mean, it's got like the stripes on its head and the thing on its eye. And So the network says, I think this looks like that. And this is a prototypical clay-colored sparrow. I've seen a bird like this before. It was in my training set, and I know this bird. And then the network also says, well, look over here, the edge of the wing and the belly here, the black and the white and the brown, all of that looks like this part of that bird. And that is a prototypical clay-colored sparrow from my data set. And this looks like that, and this looks like that. And so that is how the network actually reasons. It's doing a lot of comparisons of the current image to images in its training set. And it will create a score, like a numerical score for each comparison it's making. And the prototypes, all of this stuff is learned, right? There was no human who picked out these prototypes. They were all learned from data. And also the way to compare these images, that was also learned. So every computation of this network is either something that's visually checkable, like does that look like that? Does this look like that? Or it's like a bunch of numbers added up, because there are scores, numerical scores for each comparison here, and we just add them up. Okay, so because the network does this looks like that, and this looks like that, and this looks like that, we called the paper This Looks Like That. And the way the method works is it adds a prototype layer to your favorite convolutional neural network and forces the network to do case-based reasoning. And like I said, the prototypes are learned during training. So let's say, you take your favorite black box convolutional neural network, and then right before the last fully connected layer, you add in this prototype layer, which forces the network to do these kind of comparisons while it's classifying. So what the network does is it scans it convolves a bunch, and it scans the image, looking for parts of the image that look like parts of the prototypes. And we usually have about 20 prototypes per class. That number can be chosen as a parameter. And what I'm going to do is I'm going to just show you this whole computation right here, because I can write out the whole computation of that for a particular prediction. Okay, so why is this bird classified as a red-bellied woodpecker? So what my network does is it says, well, I think that this part of the bird looks like this part of that bird. And I've seen that bird before. That is a prototypical red-bellied woodpecker. And it does that comparison and gives you the similarity score of 6.499. This is a very high score, but there's a reason for that. It's because these birds look very similar, like these heads look very similar to each other, like orange, white, black, like with a curve and everything. They look very similar to each other. And then this number here is how important this prototype is to this red-bellied woodpecker class. So you have, again, one score for how much this looks like that, and then you have another score, which is how representative is this bird for the red-bellied woodpecker class. So we do this 20 times for all 20 prototypes of the red-bellied woodpecker class, and we get the total evidence, right, for it being a red-bellied woodpecker. So the total score is 32.736 points. And we do this calculation for all of the different classes of birds. And this is the second most highly scored class, which is the red cockaded woodpecker. Now, the thing about red cockaded woodpeckers is they don't seem to have red heads. And so when the network tries to compare our bird with the prototypes of the red-bellied woodpecker or the red cockaded woodpecker class, it just can't find similarities. Like they just don't look like each other that much, because the head of this bird doesn't look like the head of that bird, right? It can find some similarities in the feathers. Like the feathers kind of have like the special kind of pattern, but the head is really kind of where you get all the points. And so these comparisons, they just don't give you enough points. And so that's why we would say, okay, this is a red-bellied woodpecker. Okay, now the network doesn't always get it right. So here's an example where it messed up. This bird was incorrectly classified as a prothonotary warbler instead of a Wilson's warbler. And we used a base model of DenseNet 161, and we trained it to be we made it a proto-peanut and made it interpretable, transformed it. And it just couldn't find that much similarity with this birds in this Wilson's warbler class, even though it's a Wilson's warbler. And so we looked at, the prothonotary warbler class, because it was misclassified as prothonotary warbler. But if you look at it, this bird looks like a prothonotary warbler. I mean, maybe it's not exactly the same, but like to me, like the yellow and the sort of grayish color, and it feels like it looks like it. So that's kind of why that was misclassified. But there's more. So if we switch out the DenseNet 161 to a different base model, like here VGG16, then it actually gets the answer right. So here VGG16 correctly classified the bird as a Wilson's warbler, and it really paid attention to like the eyes and the beak and like the sort of shape of the eyes and beak, and it excluded the bird's head in the prototype. And so I think what happened is that this little cute bird might be a baby Wilson's warbler, and so it doesn't yet have this big black spot on the top of its head that it's supposed to have when it's a Wilson's warbler. And so it just can't get as many points. It couldn't get as many points for that class. And so the way we would solve this in practice is that we would retrain the model with adding in a whole bunch of baby Wilson's warblers, and then hopefully next time it will get the answer right. Now we've been playing around with this bird watching data set, 200 classes of birds. This is a benchmark data set in computer vision. The original black box accuracy is between 74% and 82%. And then if we take those black boxes, so we tried a whole bunch of black boxes, we take them and we make them all interpretable by making them all proto-peanuts. Just like I showed you, we add that extra prototype layer and retrain it. Then the model's accuracy was within right in the same range. And in fact, if we stack all the proto-peanuts together, we still get something interpretable, but the accuracy is even better than any of the black boxes. So anyway, it's pretty neat because what it's telling me is that even for computer vision, right? Even for computer vision, where the deepest of the deep neural networks are trained, we can still have an interpretable model of the same accuracy as a black box, right? I have yet had to find a domain where I actually need a black box. All right, so in any case, we were wondering, after we did this, we were wondering where we might actually use it, because, birds, okay, great. But we wanted to do something that would be helpful for people. So we decided to find some collaborators, and we found, at Duke Hospital, we found a medical physicist and a radiologist interested in computer-aided mammography. Now, as you probably know, breast cancer is a leading cause of death, not just in the USA, but around the world. There are hundreds of thousands of cases diagnosed each year just in the USA, over 300,000 in 2019, causing tens of thousands of deaths each year. And mammography is the hardest task in all of radiology. In fact, radiologists miss a fifth of breast cancers. Half of women getting an annual mammogram over 10 years will have a false positive. Up to 3/4 of biopsies come back as benign. In other words, these are potentially unnecessary surgeries. So we decided that we would help them by building an interpretable AI algorithm for mammography. So this is what we did not do. We did not create a black box approach. So this is where we take the breast lesion. So this is a breast lesion. And then the black box model would just classify it as benign and just not tell you why. If we were just doing saliency maps, we would send the lesion into the algorithm, and it would say, oh, that's probably benign. And we say why, and it says, oh, because blob. And all it did is highlight the lesion. But I already knew where the lesion was. That's why I sent the picture into the thing in the first place. So it didn't tell me any information I didn't know. So what we designed instead was, it's called the interpretable AI algorithm for breast lesions. And what it does is it takes the lesion and it sort of does a lot of comparisons to prototypes. So here, for instance, it says, oh, this part of the lesion looks like that part of this lesion. And this is an indistinct margin lesion. So that's maybe bad for the patient. So we'll add a bit of points to the malignancy score. Okay. Whereas this part of the lesion looks circumscribed. It looks like this circumscribed lesion. And so circumscribed is good for the patient. And so we'll subtract something from the malignancy score. So that's how it works. And again, this is just exactly how the network reasons. And it's doing this and showing you its reasoning process so that you can figure out what, whether you trust it or not. So we've been wondering, where, and by the way, there was no accuracy loss over the black box models. In fact, the opposite. Our method actually has to focus on the correct part of the lesion. It's not allowed to use the confounding information around the lesion. So it's actually solving even a harder problem than the black box methods, because those methods can use confounding and we wouldn't know about it. All right, so here's an example. This is the lesion. We show you where it is. We show you where the network is looking. So here it's looking at the margins. It says, well, I think this margin looks like this circumscribed margin lesion. And so that's why I'm going to add some points to your circumscribed margin score. And same here, it does this comparison and so on. Okay, and here's the paper that we've written, our first paper on computer-aided mammography. All right, so we've been wondering, where are black box models more accurate? And so, there's ways to answer these questions in machine learning. Machine learning is really good at sort of figuring out answers to how to evaluate questions. And so the first challenge was interpretable neural networks for computer vision. And as I already showed you, for computer vision, interpretable neural network accuracy seems to equal black box accuracy. And so the second challenge is sort of, really hard benchmark data sets. So if you like benchmark data sets, I'll show you a great benchmark data sets, which is the data set from the Explainable Machine Learning Challenge. And this data set comes from FICO, and it's a loan data set. So the data set is a loan decision data set. You have people's credit history, and you're trying to predict whether they will default on their loan. Okay, so the data set came with 10,000 loan applicants, all of these factors about these people's credit history. And then we ran a whole bunch of black box machine learning methods on the data set and got an accuracy of 73% and the best black box area under the RSC curve was 0.8. Okay, so these are the numbers we want to maintain. We have to keep this accuracy when we're designing our interpretable model. Now, IBM, which won the challenge, actually produced a really tiny model with only 6 questions. The problem was that they lost performance. So their accuracy dropped a little bit, but their AUC dropped a lot. So AUC ranges from 0.5 to 1. And so to go from 0.8 to 0.62, that's really quite bad. So our entry, which won the FICO Recognition Prize, it maintained exactly the accuracy and AUC of the black box. So let me tell you a little bit about this competition entry. So we didn't have access to a domain expert. We had no access to anyone from FICO. So we didn't really know what they wanted. So we went to their website, and they had a lot of neural networks on the website. So we decided that we would try to make something that looked like a neural network, but it was actually just a bunch of logistic regression models stuck together, really tiny little itty bitty models just all stuck together. So what we did was we took all the features, which are here, and then we created 10 subscales, each of which uses 4. It just uses between 1 and 4 factors. Okay, and then we put all of the subscale information together into a final logistic regression model that had only 10 terms in it. So this was, it's like these little itty tiny, little tiny models just sort of stuck together, and it performed really well. Okay, so I want to zoom in and show you kind of one of the models and show you how it works, okay? So here's this model that's right here in the middle. This is the delinquency subscale. So here it includes factors like what % of trades were never delinquent and what's the months since the most recent delinquency. Okay, so here's us calculating that score with these 4 factors. Okay, so here are the 4 factors. And so we're scoring somebody right now. So let's take a look. So here the person's percent of trades never delinquent. Now, this person had a lot of delinquent trades, and so they actually get a bunch of points for that. Okay, months since most recent delinquency. So this person had a delinquency within the last 8 months, so they get some points for that. So we add up these scores, and then that's this number, add it to a bias term, and send it through this logistic function to get to the risk score, which is 79.8%. So just based on the delinquency information, this person has like a 79.8% chance of defaulting on their loan. All right, so so that's how it worked. It was really just like a bunch of like little tiny models like this. This is one of our bigger models too. It's so tiny. And we just glued together a bunch of these little tiny models and that was it, right? And we got the same accuracy as the best black box. All right, so yeah, the interpretable model's accuracy still is equal to the black box accuracy for even these really hard benchmark data sets. So there really is no scientific evidence that there's an interpretability accuracy trade-off at all, right? You don't need to sacrifice predictive performance for interpretability as long as you're good at optimization and can optimize for interpretability in addition to accuracy. Okay, so we were very proud of this, competition entry, and we were very excited about it. And we were told that, we wanted to submit it to a special issue of a journal. And we were told that we needed to email the editor of the special issue before we submitted it to make sure that the paper was in scope. So we sent an email over to the editor. We said, dear Fancy Esteem Professor at Fancy Esteem University, we wrote this paper based on this model, and we did an inherently interpretable model. We don't know whether the paper fits into the scope of the special issue. It's not a traditional methodology paper. Its contribution is an analysis of the FICO data, including a machine learning model that's interpretable, and you don't need a black box and blah, blah, blah. The paper's content won this nice prize that they gave us. And the guy wrote me back, and he wrote, Dear Cynthia, thanks for reaching out. This is an interesting paper, but I'm afraid it's not a good fit for this special issue. It's also related to my own recent work on explainability of neural nets. Is the FICO data still available? And if so, could you share it? And I was just like, oh gosh. I sent the guy a paper saying, you don't need a black box model for this data set. And he sends me back an email saying, I don't care about your work, but can you just send me the data so I can create a black box and explain it? Sometimes people just don't get it. So finally, I got sick of all of this nonsense, and I finally wrote a paper called Stop Explaining Black Box Machine Learning Models for High Stakes Decisions and Use Interpretable Models Instead. And it had please in the title earlier, and they made me take out the please. Like it was like, please stop explaining. So it was kind of more polite. So now it sounds more commanding, like stop doing this. And I gave a lot of reasons, and so I will tell you some. So first, black box models still force you to trust the data set. No matter how you explain them, you still have to trust the data set when you're dealing with a black box because the computation is so complicated that you have to make sure that all the data that went into that model is trustworthy, which, I've never met a big data set that was trustworthy ever. There's also this problem that I call double trouble, where it forces you to rely on two models instead of one. Black box, explanation. And if either of those models don't work, you can't trust it. Because if the explanation method doesn't work, you can't trust the black box. Now, these two models have to disagree with each other. Because if they don't, you can just remove the black box and just use the explanation as an inherently interpretable model, right? They're equally accurate, so you might as well just use the explanations as the model itself. So they have to disagree with each other. So let's say that they agree with each other 90% of the time. Well, that means that it's wrong 10% of the time. That means 10% of the time you can't trust the explanations, which means 10% of the time you can't trust the black box. And that 10% of the time is probably the cases you really care about. Now, also, the word explanation is loaded. sometimes these, what they call explanations, are not actually explanations. They don't actually use the same variables. And there's even been a scandal where it was the ProPublica scandal, where ProPublica said that this criminal justice model, COMPAS, they said it depended on age, criminal history, and race. But their analysis was wrong, because what they did was approximated COMPAS with an approximation model that depended on race, and then claimed that COMPAS depended on race. And so, you can't do that. That's not, you think you've explained it, but the truth is that you use totally different variables than the underlying model, right? You created an approximation, not an explanation. And then finally, I think the most powerful argument in favor of black box, in favor of non-black box models, in favor of inherently interpretable models, is that if you can produce an interpretable model, why should you explain a black box? Do you really want to extend the authority of the black box? You could simply replace it with something that was more interpretable. And anyway, do we really want to extend the authority of the black box? For high stakes decisions, you really don't. All right, so these are the papers that I spoke about in my talk. This is the Please Stop Explaining paper. This is the 2 helps 2B score. This is the method that created the 2 helps 2B score. This paper is our latest paper on decision trees. So this is, I mentioned the Corals algorithm earlier. This paper is kind of like where we've gotten to on decision trees. It's our latest machine learning method on that. Then this paper is our paper on interpretable deep neural networks with prototypes. And here is the application to mammography. And then this paper over here is a review paper. So if any of you are mathematicians or computer scientists and you're really interested in finding out, or students, and if you're really interested in finding out about what the major technical problems are in interpretable machine learning, you can go ahead and check out that review paper. So thank you very much.